All right, welcome students. In this lecture, we'll be dealing with the derivation of Planck's law. As I have shown you earlier, what was the basic assumption and what were the basic conditions through which Planck had undergone, and he used as I told you, he used these statistics called as the Bose-Einstein statistics. Bose-Einstein statistics for the black body radiation. Okay? And in the previous lecture, I have shown you that from this very statistics, the Bose-Einstein statistics, we get the number of particles inside a specific energy state with a specific energy. The number of particles inside that very state is given as to be equal to Ni is given to be equal to the number of phase space cells divided by e to the power beta by u, that is the energy of that very state, ui divided by beta minus 1. This was the formula which was derived in the last lecture, as you can check out that very lecture also. This is the basic formula from which Planck started. So this is the this formula is actually the Bose-Einstein statistical formula, which says that for any photon gas, the number of particles present inside a specific energy state at any instant can be given by this very formula. So if we consider a frequency range from nu to nu plus d nu, that is for a short interval of frequency range ranging from nu to nu plus d nu, the number of particles within this kind of range of frequency, those number of particles having the frequency range of d nu, that will be given as n. Say we will represent these very particles which are having the specific frequency of d nu within the range of that very frequency will be represented by n nu, d nu. This will give the number of particles in that very state to be equal to, from this n nu d nu, then there will be the number of phase space cells within that frequency range also, and that will be represented as g nu d nu whole divided by e to the power ui, and that will be the energy state within this very frequency range. U divided by, we can still represent it by I, which represents in the specific energy state, e to the power I divided by beta, and this is not the formula, its formula is like it's not divided by beta, it is beta ui. Sorry for that, you can check the earlier lecture also, it's beta ui. So beta, I have told you earlier that beta is equal to 1 upon kT. This was used as the Lagrangian multiplier in the previous derivation, wherein we can derive by using the method of Lagrangian, from which we can find this very beta. This is the Lagrangian multiplier. So that comes out to be equal to 1 upon kT. This is already, you will be known about it from your previous classes, from the thermodynamics, statistical thermodynamics in specific way. So using this very thing here, we can get beta, this very thing to be equal to u divided by beta, multiplied by beta, which means it is 1 upon kt, 1 upon kt minus 1. So this will be the number, this will give the number of particles which are present inside, which are present in a specific energy level, energy state within the range which having the frequency range of this very thing, that is d nu. Okay, so what can we further do with that? What Planck did, we know that we have already taken this very thing which was derived in the previous lecture. You have seen that we have taken a momentum space. Okay, a momentum space, for example, this is px, the momentum along the x-axis, or the px is the coordinate system in the phase space coordinate system. Here will be py and this will be pz, or whatever you may choose it. Okay, in that very coordinate system we took a spherical shell. In the previous lecture we took a spherical shell having the radius of momentum. This very spherical shell will be having the radius of p. If the width of the spherical shell is dp, then the outer shell will be p plus dp, of radius p plus dp, p plus dp. Then in that case we get the number of phase space cells within the range of momentum p to p plus dp, that is the momentum range will be dp. Okay, so in that very case the phase space cells, you have already seen that, was given by gp dp equal to this is all done in your previous classes. These are all the formula which I use here. You can check it out from your previous class, previous thermodynamic subject, wherein you will get these very formulas, and this very formula, this very thing, that is the number of phase space cells in the range of dp, is given to be equal to the volume, that is the special volume, multiplied by the volume of phase space, volume of phase space, divided by the volume of a single phase space cell. Okay, phase space cell, and that is equal to h cube. Kindly rewind your previous knowledge about the thermodynamics, you will get that. It is not some rocket science. I'm using the simple definition of number of phase space cells from your previous knowledge of the thermodynamics. And that very is given to be equal to, that is equal to the volume of special coordinate system which is undertaken by the black body, which is under discussion. That is the volume of that very specific region, the V, multiplied by this volume of the phase space. It is represented, we can represent it like dpx, dpy, and dpz, which I have shown you earlier, the volume of phase space, whole divided by volume of each phase space cell, which is equal to h, that is the Planck's constant cube. So this will give us the number of phase space cells in that very specific range of momentum dp. So you have seen it. We can deduce this very thing from that very diagram which I have drawn earlier, that the volume of this very phase space is, as you know, the volume is given as to be equal to 4/3 for any sphere, 4/3 pi r cube. Okay, and here the radius which we are taking here, it is in the momentum space. So that means we'll be writing this instead of r, here it will be momentum. So if we take a small range of volume, that is for that very spherical shell which I have undertaken earlier. So for that small spherical shell, the small volume will be given as to be equal to 4 pi p square dp. Simply differentiating this very thing, we will get 4 pi differentiation of pq will be 3p square, and 3 and 3 goes, we will get 4 pi p square dp. Cool. I think this is very much simple. So using this very thing here, so we will get dv, that is this very thing, the volume of that very specific phase space will be given as 4 pi p square dp divided by this very thing. So we will get this gp dp, that is the number of phase space cells within the range of dp, will be equal to v multiplied by 4 pi p squared dp, that is this very thing, dp whole divided by h cube. So this will be our phase space number of phase space cells within the range of dp. Similarly, if we take this very thing in terms of frequency, if we take the number of phase space cells here, it is in terms of the momentum. Now we will take within the range which we have considered earlier, the frequency range of nu to nu plus d nu. Then this very thing, the number of phase space cells in that very range will be given as to be equal to g nu d nu, that is the number of phase space cells within the range of nu to nu plus d nu, that is this much of frequency range. That will be given as g nu d nu will be given as to be equal to this very thing, but here we are getting the momentum. We have to change that very thing into the, we have to convert function of p here to function of nu. So for that, what we will do, okay, kindly make the use of the previous knowledge. This very equation, you have to remember this very equation. I will write it down here first because this will be used later on. We are getting n nu d nu equal to g nu d nu. This was divided by e to the power ui by kt minus 1. This very equation will be used in furthermore by using gp dp inside this. So right now we are having the equation, we are having the number of phase space cells, with respect to the momentum, but we have to change that very in terms of the frequency. We know from the special theory of relativity, from Einstein's special theory of relativity, what does that say? We have a formula in that very theory which says that energy of a photon or energy of anything which is under discussion will be given from the special theory of relativity is given as to be equal to under root of p squared c squared plus mass of that very particle, that is the rest mass square multiplied by c to the power 4. This is the formula for any particle exhibiting that much of energy. And here we are studying the Planck's law for a black body. So black body, we are studying actually the photons, the radiations emitted by the black body. So here under discussion, the particle here is photon, that is the light, and we know for light, for a photon, the rest mass, that is m0, is equal to 0. Okay, this m0 is equal to 0. That means a photon cannot exist in the rest state. Fine. So the mass of the photon, rest mass of the photon is 0. So that means we will get E equal to under root of this very term vanishes. So we will get under root of p square psi squared, which in turn means that E equals what? Pc. Okay. And from Planck's postulate, we also know that from Planck's postulate says that, it says that within that very black body which is under discussion, the number of photons which are existing inside it, these are having a quantized energy, and those photons are actually called as the quanta, and they bear a simplified kind of quantized energy within them, and that very energy is given as to be equal to E equal to h nu. Fine, this is already known to you, and I have said to this very thing in the earlier classes also, that Planck's postulate is that the energy of the photon is quantized and is given as to be equal to E equals h nu. So we will get from these two cases that h nu will be equal to Pc. That means Pc will be equal to h nu. So this will give the relationship between the momentum and the frequency, which is under discussion. So here it was this phase space cells Gp dp was a function of momentum, but we will change this to the function of frequency by using this very thing. So our momentum will be equal to here h nu. Sorry, momentum will be equal to c h nu divided by c. H nu divided by c here. Simple, cool. So using this very thing here in this equation, so what will be the result? This is, I think, very much simple to understand these things because it is using the basic concepts still. I'm not using that much of hoo-ha from the imaginary kind of stuff. It is all known to you in the previous, from your previous knowledge of the previous subjects, that is thermodynamics and special relativity. From the classical mechanics, I'm using this stuff. So you must be known about it. Now, using this very thing here, so we will get this number of phase space cells in terms of frequency. So our number of phase space cells in terms of frequency will be given as G nu d nu will be given as to be equal to 4 pi v multiplied by p squared. What is p squared? First I will divide by h cube, and our p squared will be equal to h squared nu squared divided by c squared. So we'll get p squared, that is h squared divided by c squared multiplied by nu squared. dp, what is dp here? If we differentiate this very thing, we'll get dp equals h is constant, c is constant, so this will be written as it is, multiplied by, we'll be differentiating with respect to frequency. So our dp will be equal to h divided by c divided by d nu. Fine. Cool with that? Okay. So here h squared and h cube, h squared vanishes. We are getting the result as 4 pi v divided by h cube, and h cube goes, we'll get c squared, and c is c cube. What is remaining behind? It's v nu square d nu. Okay, this is the number of phase space cells for a photon, but we know for a photon, for every photon, there is always a possibility that for a photon, it always exhibits two kind of polarizations. There are always two kind of polarizations possible, two polarizations. So with a photon, there is the affiliation of two polarization, that is left-hand sided and the right-hand sided photon, left hand and the right hand polarizations. Either photon is a left hand polarized or right hand polarized. So there is always affiliation of two polarization with a photon. So the number of phase space cells is always twice the number of photons, because the polarizations are always double to that of a photon. With each photon there is affiliation of two polarizations. So we have to multiply this very thing with 2. Okay, so we will get the end result of the number of phase space cells to be given as g nu d nu equals 8 pi v divided by c cube nu square d nu. Okay, this is the number of phase space cells. And now, till now, is it fine for you? So we are getting the number of phase space cells. Now we are using this very thing in this result, which we have derived in our previous class, in our previous lecture, where we have derived the number of particles in a specific energy state will be given by Bose-Einstein statistical formula, which is written here. So kindly use this very thing into that. What will be the result? I hope you are getting it very much clearly, and with these kind of relations, or you have to deal with these kind of relations with whole of your in the quantum mechanics. You will be dealing with such kind of stuff, so you have to be prepared for that. Kindly use this very thing into this to get the number of particles present within a specific frequency range. So now our number of particles within the range of frequency d nu will be equal to, as I have told you, we have to convert this very function of p to nu, and we have did that. That is done here. Now we are using this very thing, g nu d nu. G nu d nu is equal to this very thing, that is 8 pi v divided by c cube multiplied by nu squared d nu. D nu is already there. D nu divided by this very thing. That means multiplied by 1 divided by e to the power ui by kt minus 1. Cool. Okay. So this is the formula for number of particles within the range of d nu. So this is the total volume. Kindly shift it on this side. We will get this very thing divided by v. So number of particles divided by volume. What is this very thing called as the number density? This is the number density of particles in a specific energy state within the range of the frequency of p nu to nu plus d nu, that is within the range of the frequency of this much. So that will be given to be equal to 8 pi divided by c cube nu squared d nu. This is the number density, and we have to calculate from what the derivation of Planck's law actually is. We have to calculate the energy density of the emitted radiations or the absorbed radiations from the black body. Okay, black body radiations. We have to calculate the energy density which is emitted from the black body. So for that, what we will have to do is that this is the number density. If, for example, within a specific energy level, say ui, this is the energy state having energy ui, if the number of photons, if the number of particles here is n times something, say this is first shell or the first energy level which is having the number of particles inside it n1, and there is some other shell, another level with energy u2, the number of particles inside it is n2. Similarly it goes on. So what will be the energy affiliated with all of these particles here? The total energy of this very state exhibiting the energy with each particle ui, and the total number of particles is u1, and the total number of particles inside this very state is n1. So the energy will be equal to n1 times total energy is n1 times u1. Okay, similarly with this second shell, with the second state, the energy will be equal to n2 times the energy of each particle in that very state, that is n2 times u2. So the total energy will be equal to n1 u1 plus n2 u2. Similarly it goes on. So that means what I have to say is that the total energy is given as to be equal to the number density, that the number of the particles in that very state, times the energy of that very specific state. Here we have the number density of a specific energy state. So in order to calculate the energy density, what we will have to do, we will have to, similarly as we did here, we have to multiply this very number density with the energy of that very state, with energy which we know that for photons the energy is quantized, and that very energy is given as E equals h nu, because we have considered the frequency range of nu to nu plus d nu. Okay, so we have to multiply for the specific problem. This specific problem, we have to multiply the number density with that much of energy, which is having the frequency of nu, and we know the energy is given as to be equal to E equals h nu. So multiplying this very thing to this very equation, when we do that, what will be the result? The result will be here. This is the number density. Till now we are getting the number density. When we multiply this number density n with the energy of that very state, we'll get the energy density. Energy density will represent that very thing with E rho, or something you may call it E rho or ED, that is the energy density, will be equal to this 8 pi divided by c cube, 8 pi divided by c cube, 8 pi divided by c cube multiplied by nu squared d nu, and we have to multiply this very thing by h nu, that is E, and h nu multiplication will result in h here, and nu will multiply to this very h nu square, will get nu cube. Okay, cool. So this very thing will be the energy density, which was derived by Planck, and this very thing is called as the Planck's law. This is the Planck's law for the radiation of black body. Planck's law for black body radiation. What here, the end result is that now you have to remember this very equation only. Have a look upon this very equation. What you think about this very equation. So kindly try it yourself, draw the graph of this very thing, this very equation. Draw the graph between the energy density with respect to the frequency. Okay, try to draw the graph. We will see the graphical representation of this very equation now. Cool. So if we draw the graphical representation of this very thing will look like, if this is the energy density, okay, energy density axis, and along this very axis we will take the frequency, or in the earlier case, as in my previous lecture, in my first lecture, I have drawn the graph between the intensity and wavelength, and here we are drawing the graph between the energy density, because energy density is related to intensity. Energy density is the energy per unit volume, as you have seen that, and the intensity is the energy radiated by that very black body per unit area, per unit time. So these are related, and the graph will be compared to each other. So you will see that along this very axis we are taking the frequency nu. Okay, what will the graph look like? Here the graph will be for a specific temperature. The graph will look like this. This will be our graph for, say, temperature equal to 6K, 6000 Kelvin, okay, or something. You may, this depends upon the experimentations. We say that the temperature here is 6000 Kelvin, 6K. So for at the temperature T equal to 3K, say for instance, we'll get like this. And for other thing, for T equal to 3K, similarly for K equal to 2K, sorry, the peak will shift towards left hand side. Keep that in mind, because if the graph is drawn between the intensity or the energy density and wavelength, then the graph will shift the peak towards the right side, and in case of here, with respect to frequency, the graph shifts towards left side. Okay, this will be the graphical representation, which is derived, which we draw from using this very equation. And see, this was the experimental data. If we check it out, as I have told you in the previous lecture also, this was the experimental data which was derived for the black body. But classically, in the classical, if we consider the wave theory of the light, here we were getting the relation between the intensity and wavelength, or we can say the energy density. Here it was related to wavelength as 1 upon lambda to the power 4. So that means, which is in some aspect, because we know that the wavelength and frequency are related to each other as inversely proportional to each other. So that means this I should have been proportional to the nu 4. Okay. But this should have been, this could have been right if there was a graphical representation where this very portion was missing. If we were getting a graph like this, like this, then this should have been in accordance, then this is in accordance with the classical wave theory of the particles, classical wave theory of photons. But in case of here, if we consider this very equation, for shorter frequencies, say for shorter frequency, if frequency is very much closer to 0, that's for shorter and shorter wavelength, for shorter and shorter frequencies of the photons. Sorry, I haven't written one term here. Sorry. I have forgotten one thing. There was some other term also, and that is multiplied by, as you might have seen, 1 upon e to the power. In that case, we were having this divided by e to the power u divided by kt minus 1, and this u is actually the energy of photon, that is h nu. Okay, so using that very thing, I'm sorry for that, I have forgotten that. That is the end result will be 1 upon e to the power h nu divided by kt minus 1. This is the final result of the Planck's law. So for smaller value of frequencies, that is nu tending to 0, what will be the result? This very thing will be equal to, in that case, if we try to put this very nu equal to 0, so that will be e to the power 0, and that will be equal to 1. Fine, and 1 minus 1, it will be blown off. Okay, so in that case, when the frequency is very, very low, this very term dominates. Fine, this very term dominates, and the domination is given by this very term, that is nu cube. And nu cube, when this very term is very, very smaller, we will get the end energy level and energy density will be very much smaller. Okay, because our frequency is smaller, the dominant term will be nu cube. If the nu is smaller, then our energy density will be smaller also. So which is seen from the experimental data also, because if we decrease the frequency, we will see that there is a decrease in the energy in the energy density also, which is in accordance with the Planck's formula, Planck's law here. Similarly, for the higher frequencies, if frequency is very, very high, that is for the higher frequencies, this term is dominating, because for higher values we have, if high terms we raise to the power something n, and this n is very much higher, then this is an exponential, there is an exponential increase, and this very term dominates at that time. So when this very thing dominates, that is for higher frequencies, we will be getting the larger value of this exponential form, and some larger value minus 1, doesn't matter, we'll get 1 divided by the larger value, and 1 divided by some huge quantity of value of some number, 1 divided by some huge number, will tend to be equal to 0, will be very much smaller. Okay, so this will be very, very lesser, smaller than 1. So in that case, we will get, again, the energy density will be lower. So that means if the frequency is again increased to some larger values, then the energy density will again be lowered, because in that case, this exponential term will dominate, not this nu cube. For example, we are having these two, we're having these two terms here. One is nu cube and other is e to the power nu here, e to the power nu. Other things are constant, so keep that aside. So if we take the larger values of nu, say for example 100 to the power cube, we'll get a number 10 to the power 6. Okay, but this is almost greater than this. E is equal to 2.14 something. So taking this as 2 to the power nu, and nu here is 100. And if you get this very result, and this will be very much huge than this very term. So for that means for larger values of nu, the dominating term will be E. Okay, so in that case we will get the lower in the energy density, which is in accordance with the graphical representation, which was done by experiments. And similarly for the lower frequencies, this term will be dominating, because this term will get equal to 0, will get in that case equal to 1, so with that will vanish in that case, and the dominating term will be this nu cube, and that will again be a smaller quantity. So that means again the energy density will be smaller in that case also. So there are two extremes in case of this very energy density. On either side of this very peak, we will see a depth, we will see the lowering of the energy levels, energy densities, or the with the energy density, the energy radiated by the black body will be, we can say, the most probable density, the most probable state will be this very thing having a frequency range here, and on either sides of this very frequency, if we increase the frequency, the number density or the energy density will be lowered, and if we decrease the frequency, then in either cases the energy density will get decreased. This was the experimental data, and this was the law derived, the formula derived by Planck, which is called as the Planck's law, and these two are in accordance with each other. So that means there is a there was the law which is called the Planck's law, which assumed that a photon is having a particle nature, the quantization of photon with having the energy of E equals h nu. This was the basic and fundamental postulate for this theory. It suggests that the black body radiation, that is the photon, is actually having a particle nature. So it was on the basis of this very thing that we can explain the catastrophe, which was earlier discussed in the previous lecture, the ultraviolet catastrophe, in case of the experimentations observed there. Okay, so this could only be explained if we consider the particle nature of light, and the energy density of the black body radiation, which is the radiation is emitted from the black body, is given by the Planck's law, which is this very thing, E equals this very thing, where we get the exponential term and the cubic term, and this is in accordance with the experimental observations. So I think this is all for today. We will, in the next class, we will see the Venus displacement theory, Stephan's law, and other stuff. This will be, I think this is very much simplified. Hope you are getting it well. Let's see what is going on, what will be going on in the next few lectures. We will be dealing with this similar kind of stuff. Hope you will get it. I will see you in the next. Thank you.